Okay, this video will attempt to explain the parent functions for the secant and cosecant functions. These are the reciprocal functions to sine and cosine. So in your notes, you've got this graph. It's not great, but we'll try to use it to, I'll try to use this to explain just the basic skills with this. Cosecant. Cosecant is the reciprocal of sine, 1 over sine. This graph will be undefined when sine is 0. So just going back to the unit circle, you can see that sine is 0 at when you're starting at 0, when you're at 2 pi, all the way around when you're at pi. So in increments of pi, this graph is going to be undefined because you would have division by 0. 1 over 0, this will be an undefined expression. So that's the reason why the graph of the reciprocal functions would have asymptotes. This is a rational function, it's 1 over sine. So rational functions have asymptotes. So this graph has vertical asymptotes. And the asymptotes occur at the places where sine would be undefined. The period of the graph is still 2 pi because you're still going around the circle 2 pi radians, but the asymptotes are a new twist to this, and then the way the graph looks is also a new twist to this. So what you're viewing here is just the basic sine graph. I've gone ahead and drawn in the asymptotes. The asymptotes are occurring at increments of pi. So I've got negative pi, 0, pi units apart, pi, 2 pi, 3 pi. So go ahead and draw in the asymptotes in your notes. And the asymptotes occur when sine x is undefined. And that's going to happen the way that you would say this happens at 0, it happens at pi, it happens at 2 pi. But a way that you would mathematically say this occurs when x is a multiple of pi. So n pi, where n is an integer, and the capital letter Z is the abbreviation for the number set of integers. So that's the way that you would describe all of the asymptotes. We'll talk about the range in just a minute. So go ahead, map out the asymptotes and try to wrap your head around the idea that you have asymptotes, because these are the places where you would have a ratio with division by 0 if the graph were able to cross. So this is the sine graph. You're looking at the sine graph. The way the reciprocal graph looks, though, the reciprocal graph looks like this. Here I'm at a maximum point. It's curving away. So it's little kind of parabolic shaped curves between each asymptote. Here it's a minimum, curving away. And here I've got another peak. So I'm going to curve up away from, and that's a curve. That one doesn't look very curvature. And here I've got a minimum point. So I'm going to curve down. The graph that you should just be viewing would be the red with the asymptotes and then the red ink. The sine graph, the parent sine graph, is in there just to give you a frame of reference. It's always helpful to have the parent graph sketch because it helps you kind of figure out where the asymptotes are, as well as where these branches, these parabolic shaped branches occur. This is the parent function for the cosecant. The range for this is, oscillating. Let's see, this is -1. And then here, this maximum value is +1. Here I have +1 and -1 on the y-axis. So the range for this is -infinity to -1, soft bracket, hard bracket, and you would union that with 1 to +infinity. So this graph is turning away from the x-axis, and the asymptotes are help funnel the different branches in. Also, the asymptotes occur where the original graph, I don't want to call it the parent graph, but where the original sine or cosine graph cross the x-axis, or the midline, as we'll see whenever we start transforming these. The asymptotes are occurring, and you can see where I've got the asymptotes drawn in. You can see that it coincides exactly with these little x-intercepts right here. That's another easy way to kind of figure out where the asymptotes would go. Okay, let's look at the secant graph. So secant 1 over cosine, same logic, just different places in the grid where you would have an undefined expression. So secant is 1 over cosine. It's going to be undefined when cosine is 0. And of course, going back to the unit circle, that's going to happen when you're at values like pi over 2, 3 pi over 2, multiples of that pi over 2 thought. That's where you'll have an undefined expression here. The period for this is still 2 pi. So, cosine and sine have a period of 2 pi. Their reciprocals also have a period of 2 pi. The asymptotes occur where cosine x is undefined, and that's going to be at spots like pi over 2, 3 pi over 2. And the way that you would mathematically represent that, you would say x equals pi over 2, and it's going to occur in units of pi, and you would say plus n pi. That's going to take care of all the iterations starting at pi over 2. Every time you travel a pi, pi halfway around the circle, you're going to be at an asymptote spot, but you need to specify that n is an integer, and that capital letter Z represents the number family of integers. So that's a mathematical way to describe where the asymptotes occur. Also, you can see looking at the graph, the basic cosine graph, the parent graph, that the asymptotes I have sketched in occur when this graph does cross the x-axis. And that is also an easy way, a recurring theme with this. Now, to graph the secant graph in, it's the same logic. Come to a minimum point and then draw the little parabolic curves away from the x-axis and in between each asymptote. Here you're at a maximum, so you're going to curve parabolic curve up. You're at a minimum, curving down. You're at a maximum, and you're curving up. So the actual function itself would be the blue parabolic curves with the asymptotes drawn in. And it's always nice to have the cosine or sine graph there to kind of, reference you in, but that's not the actual graph. The highlighted blue or the blue curves, that they represent the graph. Range is the same. So you're going to be negative infinity to negative 1, and you'll union that with positive 1 to positive infinity. So I want you to get this jotted down, and I don't want to make the video too long. So I think I'm going to stop this video here, and then I'm going to do 2 problem examples in the next video.